In this video, we're going to learn about an important type of reaction of alcohols called dehydration of alcohols. So when an alcohol is treated with a strong dehydrating agent, such as H2SO4, along with heat, which we can represent with a triangle or delta, the alcohol is dehydrated. It loses water. And the products then are an alkene and water, the water that was lost. So if we just kind of look at a general alcohol, just represented by C with two open bonds, and we don't know what it's bonded to, doesn't matter. Bonded to another C, again, two open bonds, doesn't matter what it's bonded to. And so the first C also has an H on it, and the second C has an OH. It's that H and OH that can be lost, and the OH is, of course, just water. And so that's lost as water here on the product side of the reaction. So a general carbon chain with an H and an OH is reacted with H2SO4, so strong acid. It's heated, so we can put a little delta by its arrow. So we've got H2SO4 over the arrow. We've got delta under the arrow just to show that we need an acid catalyst and we need heat. And then what we end up with is an alkene. So now we've got CC double bond. And again, the C's are bonded each to two things, and it doesn't matter what the other two things are. As long as they have an H on one side and the OH on the other side of the two carbons, that's all that matters. So now we've got an alkene and water as our product. So again, really big picture here. Dehydration of alcohols, takes an alcohol in general, and the result is an alkene and water. And you're getting, the H on one side of the double bond and the OH on the other. And so you're going to have some sort of strong acid. I could represent that as H plus above the arrow, and you're going to have delta below the arrow for heat. So you're going to need an acid, you're going to need heat, but an alcohol makes an alkene and water using acid, catalyst, and heat. So what are some more specific examples? Well, what if we just had ethanol, CH3, CH2 with an OH? Well, the H on one carbon and the OH on the other carbon would both be removed in a dehydration with H2SO4 over the arrow. I'm going to put delta heat under the arrow. And we're going to make ethylene or CH2 double bonded to CH2 plus water. So we're taking the H off one carbon and the OH off the other and making ethylene. What about cyclohexanol, where we've got a cyclohexene with an OH? Well, you're going to remove the you're going to remove the OH, of course, from alcohol, and then you're going to remove the hydrogen from an adjacent carbon with H2SO4, strong acid catalyst, and delta for heat, and you're going to make cyclohexene, ene for that double bond that's present in the ring, right? So you're going to make an alkene, and you're going to also lose water. So those are some examples of dehydration in alcohols. So let's try some ourselves. Here we've got CH2 with an OH on it, and then that CH2 is bonded to CH, which is bonded to two different CH3s. So we've got OH, CH2, CH, CH3, where that last CH, the second to last carbon, it has a CH3 group coming off of it. And it's going to be reacted with H2SO4 and delta for heat. And so what are our products going to be? Well, off of that first carbon, we're going to remove the OH. Off of that second carbon, let's drop out the hydrogen coming off of that second carbon. We're going to remove that H as well. So what are we going to end up with? Well, we're going to end up with CH2 that's double bonded to the middle C. And remember that middle C had two CH3s coming off of it because it's got that branched methyl. And then don't forget that we also produce water. And so that's our major alkene product. We've made that double bond right where the OH is to an adjacent carbon. Okay, let's look at the next one. We've got CH3, CH2, CH2, C. Now this C has an OH coming up and a CH3 coming down. And then the next CH has two CH3s coming off of it. So some branching. And it's going to be reacted with H2SO4 and delta, or heat. So we know this is a dehydration reaction, acid-catalyzed dehydration. So we're going to remove the OH, and we're going to remove a hydrogen from an adjacent atom. Now, here's where it gets a little tricky, because you could remove hydrogen from the carbon to the right, which was a CH bonded to two CH3s, or there was a carbon to the left, which was a C with two H's. So either one is possible. Let's draw in. So I had CH3, CH2, CH2. I'm going to kind of redraw that. And I'm going to draw one of those H's actually coming up. So I'm just going to erase this because one H is, going down. I'm going to actually draw in the one that's coming up. That could be removed along with the OH, just to kind of show you where I'm getting this first product. That's going to be CH3, CH2, CH. Now I lost the hydrogen going up, and I lost the OH. So the third C is double bonded to the fourth C, which has a branch CH3 coming down, and it has a CH that had two CH3s coming off of it. So I've got my first double bond as my 1, 2, 3, third CC bond. So I've changed the third CC bond to a double bond because, the fourth carbon had an OH. Now, this fourth carbon has an OH. There's no reason why it can't be the fourth CC bond that's a double bond. At least there's no reason here why it can't be. So on that fifth carbon, let's kind of scribble out the hydrogen and really draw it coming down. This time, I'm going to remove the OH and the hydrogen on the next or fifth carbon. And so what's this product going to look like? Well, I have to copy everything sort of leading up to it. CH3, CH2. That CH2 is now left intact. And the next carbon, the fourth carbon, is going to be double bonded to the fifth carbon. Don't forget that the fourth carbon had a methyl coming down, and the fifth carbon has two methyls coming off of it. Now, we need to talk a little bit about what products are actually formed. The second product that we drew is actually called the major product. And there are some rules dictating this, and they're about the intermediates and making a nice, stable intermediate. I'm having trouble circling the whole second product here. My circling looks a little wacky, but the second one we drew is actually the major product. And the reason being is the major product here is the double bond that is what we call the most substituted, or really has the most other carbons coming off of it. So the second product that we do, CH3, CH2, CH2, C double bonded to a C. The first carbon of the double bond had one methyl coming down. The second carbon of the double bond is connected to two other methyls. And so essentially, both carbons of the double bond are connected to carbons. Both carbons of the double bond are connected to carbons. Neither carbon of the double bond is connected to a hydrogen. Whereas if we look back at our first product, it was CH3, CH2, CH, double bonded to a C that's bonded next to a CH3 group coming down, and then the chain continued from that carbon of the double bond to a CH that had two CH3s. The trick really is that first carbon on the first, left side of the double bond had an H that it was bonded to. And so that's really reducing the number of carbons that an alkene carbon is bonded to. So the second carbon of the double bond was bonded to two carbons, but the first carbon of the double bond, that was bonded to one carbon and one hydrogen. So that's going to make this our minor product because it's the more substituted substituted with other carbons product that's formed, it's going to make what is a more stable intermediate in the middle of the process. I'm just going to erase here so that I have more room to do the last problem. So in our last problem, we've got CH3 bonded to a C that has an OH coming down and a CH3 going up, and then the carbon chain continues, CH2, CH2. So we can remove this OH. Oh, and by the way, it's going to react with H2SO4 and delta heat again. So again, dehydration. What I can do is on the right of the alcohol, the carbon, we've got a carbon with an alcohol. The next carbon, I'm going to show one hydrogen coming down. These can both be removed. So what I'm going to do is redraw. I'm going to draw a CH3 bonded to a C. It has a CH3 coming up. It used to have an OH going down, but now that's removed, so that second carbon in the main chain has a double bond to the third carbon in the main chain, which now just has one hydrogen instead of two, and then it ends in CH3. So I've got CH3C with a methyl group coming up, and then double bonded to CH and CH3. And then I probably have another product formed here. So what if I remove a hydrogen from this first carbon? I can kind of change that to two hydrogens. I can remove a carbon from the first hydrogen and the OH from the middle carbon. Or excuse me, I can remove a hydrogen from this first carbon. That's what I meant to say. And an OH from the middle carbon. And so this time I would have the double bond right away. I would have CH2 double bonded to that C. It's lost its OH, but it still has a CH3 group coming up. And then it has a CH2 and a CH3. And so what I notice here, if I look at what's around my double bond, in the molecule I just drew here, my first carbon of the double bond is actually bonded to two hydrogens. So that's not very substituted. And the second carbon, so this one's bonded to two hydrogens, and the second carbon is bonded to one carbon, or excuse me, two carbons. So here I have got, I'm bonded to two C's, and I'm bonded to two H's on the other side of the double bond. And in my first molecule, and if I wanted to, I could sort of redraw that as well. I could show I'm bonded to two H's on one side of the double bond, and then I'm bonded on the other side of the double bond. I'm bonded to a CH3, and I'm bonded to a CH2, CH3. So if I'm looking at, what is coming off of my carbons of my double bond, I've got two carbons, and here I've got two hydrogens. And it's better to be bonded to more carbons, recall. So that would be ideal. Let's look back at our first drawing, CH3, C, double bonded, CH, CH3, and don't forget that that first carbon of the double bond was bonded to another methyl group. So the first carbon of the double bond has, what looks like two methyls coming off of it, bonded to two carbons. The second carbon of the double bond has one methyl group coming off of it and one hydrogen. And we could sort of, draw these separate as well. We could draw CH3, C, CH3, double bonded, and the C has an H, and the C has a CH3. So I've kind of redrawn each of these as I went, but I'm connected to one carbon, one hydrogen, and I'm connected to carbon and carbon. So all that to say, these two ways that I drew a middle double bond is better, right? This is our major product, and I've drawn it twice. But that's our major product, and here is our minor product. Our minor product had our CH2 double bonded to C with a CH3 and a CH2 CH3 because it only has two carbons around the double bond. Our major product has CH3C double bonded to CH, CH3 because that first, C of the double bond also has a CH3 going up. So it has the first carbon of the double bond has two carbons bonded to it. The second carbon of the double bond has 1 carbon bonded to it. So if you want to look at carbon bonds around, the double bond, 3 carbons here is better than, in the major product, is better than 2 carbons in the minor product. And that's what we're really looking for. So all that for the last problem to show our major product.